let's make a start. We're going to start at the very beginning and we're going to talk about numbers. It might surprise you that there are different kinds of numbers, and so we're going to investigate a few of these different kinds of numbers. So the natural numbers are the things that we learn when we learn how to count. So we teach kids 1, 2, 3, you know, 1 apple, 2 cars, 3 trees, whatever. And these are called the natural numbers. We've got this cool symbol that we use for natural numbers, this guy here, and it's an N that has 2 bars at the beginning and a straight line. So it means the set of natural numbers. So what are some examples of natural numbers? Well, you can see them there. 1, 2, 3, 4, 5, and so on. So 17, 153, any positive number you can think of. So they're not very exciting. They're good for counting objects, but that's about it. So from there we go on to what are called the integers, or you might have also heard referred to as whole numbers. So integer is just a Latin word that means whole number, and they're a bit more exciting because they encompass the negative numbers as well, along with our special number 0. So the integers are a funny looking Z, which I can never draw. So kind of like that is Z. Alright, so examples of the integers: negative 17, 153, I kind of like that one, 22, you get the idea. Still not very exciting. Rational numbers are where it starts to get interesting, and the definition here requires us to pay a little bit of attention. So rational numbers are often what we refer to when we talk about fractions. Alright? So what's an example of... Hey, oh my God, I'm outdoing myself today. So, fractions. So, someone give me a fraction. I don't care.
3 over 4.
3 over 4. Beautiful. Integer top and bottom. So, that's what this means. Quotient of integers. Integer in the numerator and the denominator. And we can express it here as a fraction, and we can also express it as a decimal number. 0.75. So rational numbers can be expressed as a fraction with integers top and bottom, or as a decimal number. And there's something else about the decimal number thing. Either the decimal number stops, it terminates, or it goes forever. Okay? No, I take that back. It terminates or it repeats. So this one terminates at 5. The only numbers after here are zeros, which we wouldn't write in. But there are other numbers that repeat. So let's see. A sixth is 0.1666, and that 666 goes forever. So the 6 repeats. So there is a way to write this so that we don't have to write all the 6s. We put a bar over the 6, and that means that 6 goes forever. And it's not just the last digit that can repeat as well. So let's try one more. 1 on 11 is 0.0909. So it's the 09 that repeats. So we'd put the bar over the 09. Like that. Hey. Now here's a question. Can integers be expressed as rational numbers? What do you think? Maybe not sure. There's a quiet yes. Yeah, they can. They can. What about 7? I can write 7. My 7s have crosses through them, by the way, as 7 over 1. It's a quotient of 2 integers. So integers can also be written as rational numbers. So natural numbers can also be written as rational numbers. All right, good. Now, if a number is not rational, it's irrational. So what has to be true for a number to be irrational? You can't write it as a fraction, and the decimal numbers go on forever. Does anyone have a favourite irrational number? Yeah?
Pi.
Pi. Beautiful. It's my favourite as well. Pi. So pi is 3.14159929, and that's all I remember. But some freaks remember hundreds of digits of pi. Oh, enthusiastic people. All right, so pi is an irrational number. You can't write it as a fraction, and the decimals go on forever. Let's see, what else? Here's one you'll find a bit in this course. The square root of 2. 1.14, that's all I ever remember. 142 something, something, something. Can't write it as a fraction. In fact, one of the nicest pieces of mathematics is proving that root 2 is irrational. But we won't do it. Don't panic. Okay. Finally, real numbers. We come up against these all the time because they're the set of numbers that are either rational or irrational. So another way to say it, numbers that you can write as decimals. Yeah? So we can write, let's see. Let's dump this crap. All right, let's do real numbers over here. Numbers you can write as decimals. So we've seen a bunch of examples, but don't forget that you can write integers as decimals as well. The decimal component is just 0. Okay, great. So let's move on to example 1. Can you give an example of an integer that is a natural number? 1. Perfect. Anything that's a positive integer is also a natural number. Can you give an example of an integer that is a rational number? Integer that's a rational number. Oh, there's one up there already. 7. 7 on the left is an integer, and on the right I've written it as a rational number. A rational number that is not an integer. So you can write it as a fraction, but it's not a whole number. Ideas? A half, maybe, is what I heard. 3/4. So let's just go on to where we're actually looking. See, so don't panic if you don't get it all down, because it'll be in the recording. Okay, a rational number that is not an integer. So a half, because we can write it as 0.5, so it's a rational number, and it's certainly not an integer. An integer that is not a rational number. Can you give an example of an integer that is not a rational number?
Square root of 16.
Ooh, nice.
0.
Oh, even better. Oh, God, can of worms. All right, hang on. So Jack, I think, said square root of 16. Square root of 16 is actually 4. And I can write it as 4 on 1. So nice try, but no, 0. So yeah, this one doesn't count. This is not an example. It's a non-example. 0. But good suggestion. Can I write 0? 0 is an integer. Can I write 0 as a rational number? Can I write it as a fraction? I can write 0 as a fraction in an infinite number of ways. 0 on 1 is 0. 0 on 2 is 0. 0 on negative 1 is 0. 0 on any integer, as long as it's not 0, is 0. So this is a non-example too, but it's a really good thing to point out right now. All right, 2 really good suggestions. We haven't got an example yet. Maybe there isn't one. There isn't one, right? Can you give an example? No. We said before any integer can be written as a rational number if we divide it by 1, right? So there is no example of an integer that is not a rational number. Lovely. Great. So we're getting a sense of how these things fit together. So we can draw a diagram that shows how these sets relate to one another. Be very careful about how you say that word. All right, so here we go. Every natural number is an integer. Every natural number is a rational number. Every natural number is a real number. So the natural numbers, the set of them are inside the set of integers, which are inside the set of rational numbers. But numbers are either rational or irrational, so they don't overlap. That's why they are separate parts of this diagram. And real numbers are either rational or irrational. So the whole set of real numbers falls into one of these two categories. So let's see. We've got a few numbers down here in different forms in example 2, and I want to see where we can put them in this Venn diagram. Let's not start at the beginning. Just let's pick the one that looks the easiest. That's a good way to start. What's the easiest one we can do here? Oh, I'm going to pick 7. Where does 7 go? 7's a natural number, and it's an integer, and it's a rational number. All right, another easy one. 0, maybe? Is 0 natural? Did we decide? No? So 0 goes up here. What else? -4, good. -4 is an integer. Are there any other integers on here? Square root of 9, which is really 3. So up. Yeah, like that makes sense. So I'd put that in there. All right. Anything else you're going to put on this diagram?
-3/4.
Yeah, where are you going to put it? Oh, is it a whole number? No, it's a fraction. So he goes out here. Okay, so 0.6 recurring is a rational number because it's a repeating digit. So it goes here. See, we're getting down to the tricky ones. What else can we put in here next to 0.6 recurring?
So 0.3, isn't it?
Yep, good. 7.3. All right, now it's getting harder because some of these we don't know what they are. All right, so let me tell you. Sine of pi on 2, does anyone know what its value is? Sorry? No, I'm not being very fair to you. This one's value is 1. So we're going to, I don't expect you to know it. This one's value is 1, so we could actually put it in integers, or in natural numbers. This guy, sine of 1 degree, is some weird looking fraction, decimal, so I didn't expect you to know all of these. Pi on 2, so pi is 3.14 and something, so this is 1.8-ish, but it's not an integer top and bottom, so this dude is actually an irrational number because pi is irrational. We saw we saw root 2 before, so negative root 2 is irrational, root 3 is irrational, and what are we left with? We're left with this thing I call a number called I, and 3 minus 2i. So what's the deal with this I character? It's called an imaginary number, or a complex number, and so that's what we're going to talk about next. So real numbers are things that we can write as decimals. Complex numbers are a whole different kettle of fish, and so we'll just do a little bit of complex numbers in a tick. Not all numbers are real numbers. So we have these complex numbers, and we can write them in this special form, a plus bi. So firstly, I is this guy or girl, I'm not sure, the square root of -1. So maybe in your maths up to now, teachers have told you the square root of -1, square root of a negative doesn't exist. Not true. You can define it as the imaginary number I. An alternative definition is that I squared equals -1. So complex numbers you can write as A plus BI, where I is imaginary and A and B are real numbers. So let's have a look. 3 minus 2i is a complex number because A is shown by 3. And what's the equivalent of B here? 2 or -2? -2, because we talk about plus B. So B is -2. What about 5i? The A component is 0 and the B component is 5. Yeah? 7 is a complex number because I've just hidden 7. 7 is a complex number because A is 7 and there's no imaginary component, so B is 0. And this last two, you can see it's exactly the same. A is a half, B is √3. So they're complex numbers, and that's about all we're going to say about them in this course. But you have to, oh no, that's not true. When we do quadratics, we'll do a few more of them. So you do have to pay attention to them. Okay, so here's the thing that I want you to talk to someone next to you or think about by yourself. What do you think the relationship is between the real numbers and the complex numbers? How would you change the previous diagram to incorporate complex numbers? All right, does someone want to venture a suggestion? How am I going to put complex numbers on this diagram? Anyone brave enough? I'll do it, don't worry. Draw a big circle around here, and these are complex numbers. If you have a look at the examples we gave, any natural number like 7 we said was a complex number, so any integer is a complex number. Rational numbers, we had real numbers that were fractions, or we could write them, and they were complex numbers with a 0 component. Oh, but actually, I'm kind of not quite right. Let's just fix this up a little bit. Let me think about this. Oh no, we're good. We're good. Sorry, just having a brain fade. So all the real numbers are complex numbers, and there are guys out here that are complex but not real. So what were 2 examples from the previous slide of complex numbers that weren't real numbers? The dude I and 3 minus 2i. Definitely imaginary, but they're not real, so they're outside of all of the real numbers. Okay, good. We're going to forget about complex numbers now for the rest of today. So real numbers have a unique place on the number line. So how do you draw a number line? Here's our line that represents all real numbers, all decimal numbers, things that can be written as decimals. Here's 0, beautiful 0. And the integers are equally spaced on our number line. So you can see that's what we've done up here, equally spaced our integers. Yeah, so you've got a number line there. Numbers have both a size and a sign. So you can see the sign is being represented here. We've got negative numbers to the left of 0 and our positive numbers to the right of 0. And these guys, these positive integers and positive numbers, we're just not writing their sign. So plus 3, we just omit the positive and we write 3. Negative numbers, we obviously need to keep their sign. All right, and we use the sign of numbers to illustrate lots of things. So profit is positive, loss is negative, north is often positive, south is negative. So there are whole lots of reasons that we use a sign. All right, so I know this is elementary for some people, but it's worth reviewing. So how do you put numbers on the number line? How do you put 2 on a number line? You start at 0 and you go 2 equal units to the right, because 2 is positive 2. We move 2 steps to the right. How do you put minus 4 on a number line? It's negative, so you start at 0 and move left, and you move 4 equal steps, and you arrive at negative 4. Okay, good. We won't do all of the ones in the next example, but we can do a couple of them. So let's see. Numbers on the number line. What can we put on here? All right, some are easy. 7.3 is going to be somewhere between 7 and 8, closer to 7 than to 8. 7's already there. Negative 3/4. You have to convert it to a decimal and find its position. So negative 3/4 is 3/4 of the way between 0 and negative 1. So here's negative 3 on 4. It's not in the list, but where does pi go? Yeah, so somewhere between 3 and 4. A lot closer to 3 actually. That's kind of a bit dodge. Yeah, that didn't work. You get the idea. Oh, let's put one with a square root on there as well. So root 3 is 1.7 and a bit. So it goes in there somewhere. So you can see that even if they're represented in different forms, they still have a place on the number line. That's kind of the point we're making here. Now these real numbers are ordered by their size. So if the numbers increase in size from left to right, so these numbers are increasing as we go along the number line. And so if we want to say that 2 is less than 5, you know, the beautiful thing about maths is you can say in fewer symbols what it takes you in the English language. 2 is less than 5. 2 is less than 5. That is a less than sign. It says 2 is smaller than 5. If I want to say that 5, and you can see that 2 is to the left of 5 on the number line. So I can also say 5 is greater than 2. 5 is to the right of 2 on the number line. 5 is greater than 2. These two statements are equivalent, right? So it doesn't matter if I say 2 is less than 5 or 5 is greater than 2. These two statements are saying exactly the same thing. So it doesn't matter which way around you write it, as long as you're saying the same thing, as long as your signs are going in the right direction. Okay, good. So, less than sign, greater than sign. Things can be less than or equal to, and they can be greater than or equal to. So, let's see. We've probably got it in the next table, so let me make this go away. We'll try and rub it in an order that helps you if you're trying to catch up. Okay, here's a good example. 9 is less than or equal to 9. It's a true statement because 9 is equal to 9. But 2 is also less than or equal to 9. It's because 2 is exactly less than 9 or strictly less than 9. So we have less than and less than or equal to signs, and greater than or equal to signs. Okay, so something else for you to do in the next minute. Maybe talk to the person next to you. What I've done here is I've put a box in place of a less than, greater than, or an equal to sign. Work out which sign needs to go in the box. If you're not sure, there is no harm in using a number line. Don't feel embarrassed about drawing it out and working out which number is to the left of the other number to help you work out which sign. So 1 minute, folks. All right, so that's it. 1 minute. You might not have got to the end, but let's see how you went. So, first one, -1. Is it less than or greater than 4? Here's my number line. You're like, oh my God, stop talking. Okay. -1 is to the left of 4. -1 is less than 4. Next one, maybe not so easy. Greater than, nice. It's tricky. It's the 3 and the 4 get you. If it had been 3 and 4, the answer's definitely less than, but these negatives switch things around. -3 is to the right of -4. -3 is greater than -4. All right, next one. 1/4 and 0.2. We can only compare them if we're thinking about them both in the same representation. All right. 2 pi and 6.28. Oh, God. You just made my head explode. Okay, hang on. Don't worry, it's not that bad. Pi, remember? 3.14159. Now, as an approximation, we can round off to 3.14, but 3.14 is not its true value. Its true value is this thing that goes forever. All right? So, pi is approximately 3.14, so that's different than being equal to 3.14. All right, so if we multiply it by 2, it's exactly 6.28, but it's not, if we multiply our approximation by 2, it's exactly 6.28, but that's not what the question says. Pi is this dude. If we multiply this by 2, it's going to be just a bit bigger than 6.28. So the right answer is 6.28. Or, if you're being fancy and you're doing things other than what I asked, put an approximation sign there. It's roughly equal to 6.28. Root 2 and root 3. Which one's smaller? Root 2. You might have to use your calculator to work it out, so it's a less than sign. Great. Okay. Okay, we're going to talk about addition and subtraction on the number line, because you can see that negative numbers kind of complicate things, but we'll do it straight from the next example. So we'll kind of start here. Let's talk about adding a positive number. All right, I'm going to draw a number line. 0. Here are my equally spaced integers. I'm going to need it to go for a bit. They're equally spaced, by the way. No shame in drawing or visualising a number line. Okay, 2 plus 3. How do we work out 2 plus 3 on the number line? We start at 2 and we move 3 units in the positive direction. So, 1, 2, 3, we get to 5. And the amazing realisation that 2 plus 3 is 5. Okay, so that's pretty easy. How do you subtract a positive number? 3 subtract 2. You start at 3 and you move 2 units in the negative direction because it's a negative number. And you land at 1. 3 minus 2 is 1. Okay, pretty straightforward, I think. So let's add a negative number. 3 plus negative 2. What do? You start at 3 and you move a distance of 2 in the negative direction. So you end up here back at 1. And so you can see that those brackets aren't needed and this negative sign is overriding the plus sign. So they're equivalent statements, so we get rid of the brackets. And finally, let's subtract a negative number. 2 subtract negative 3. So we start at 2, and we want to head in the negative direction, negative 3 units. So actually what we do is we turn around and go in the positive direction. And we land at 5. So 2 negatives together like this is having the effect of making a positive. We start trying to go in the negative direction, and we want to go negative 3 units. So we start walking backwards, and we end up at positive 5. And so you can see that that's the same as just adding 3. So you can read a lot more about it in the notes. You can try the example yourself. If you're having trouble, talk to your tutor in the tute this week. And you can also read about multiplication and division on the real number line. The important thing about multiplication and division on the real number line is summarised on page 5. So we summarise by saying a positive times a positive is a positive, positive times a negative, doesn't matter which order you do it, is a negative. 2 negatives multiplied together make a positive. And similarly, you can do it for division. Why this works, you can read about it in the notes. I need a number line again. I said that all numbers have a size and a sign, and we're very happy with the idea of sign. It means you're either to the left or to the right of 0. The size tells you how far away you are from 0. So if we have a look at 2, 2 is 2 units away from 0. Negative 2 is 2 units away from 0. So when we're trying to describe the distance between 0 and our number, we call this the absolute value. And absolute value comes up so often that we're really going to talk about it now. So the absolute value is shown with 2 vertical bars either side of our number. And the absolute value of a number is always going to be positive or non-negative. What's the difference? Because distance is always non-negative. What is the difference between positive and non-negative? Does anyone know? They kind of sound like the same thing, don't they?
0.
0 is the difference. 0 is non-negative, but it's not positive. So hang on. So let's do it over here. So if you're listening in at home, positive, 1, 2, 3, 4, blah, blah, blah. Non-negative, 0, 1, 2, 3, 4. So mathematicians are very careful about whether they say positive or non-negative, and that's the reason why. All right, so let's have a crack at these guys. Hey, my number line's come back. That's good, I might use it. All right. Absolute value of 5. How do we work it out? We're trying to get rid of those absolute value signs. On the number line, it says where is 5 and what distance is it from 0. So here's 5. It's 5 units from 0. So the absolute value of 5 is 5. All right. Absolute value of pi. Pi is over here somewhere on the number line. How far is it from 0?
3.
Pi. It's pi from 0. Don't really care what the number is, it's pi from 0. So you can see that if the number inside the absolute value signs, like the 5 or the pi, is positive, all you do is take the absolute value signs away. Yeah? All right. Absolute value of negative 1/3. Where is negative 1 on 3? here, right? Negative 1/3. How far is it from 0? It's 1/3 units. So the absolute value of negative 1/3 is 1/3. Positive 1/3. It's 1/3 units away from 0. Let's do one more of those ones. Negative 3, absolute value of negative 3. Here's negative 3. It's 3 units away from 0, so the absolute value of negative 3 is 3 units. So if whatever's inside is negative, you make it positive. It can be a bit tricky to know whether what's inside is negative or positive. So let's see what's hiding under here. 2 minus pi. Is 2 minus pi negative or positive? How could we work it out?
The equation inside the lines, then work it out.
Yep, so you're going to have a look at what's inside the lines and work it out. So let's see. Jack's just laughing at me. Okay, so 2 minus pi, is it positive or negative? How are we going to work it out? Let's see. We can do subtraction on the number line. We'll start at 2 and move pi units in the negative direction. And pi is 3 and a bit, right? So it's going to take us past 0, past negative 1, and land in here somewhere, yeah? It's negative. So whatever's inside, we make it, what did we do before? We make it positive. All right. 2 minus pi. We're going to make what's in there positive. Because it's already negative, you've got to follow this carefully. We're going to do this. 2 minus pi is negative, so we need another negative sign to make it positive. So actually this guy is pi on 2. You might have to stretch your brain a bit to think about that one. Just write it down and ask your tutor, because you're going to do some more of these in the tube. Pi minus 3. Is pi minus 3 positive or negative? What's pi? 3.14 and a bit in here. Take off 3. We're going to land back here. So this guy, pi minus 3, is positive. So we can just take the absolute value signs away. All right, the last one. Need your thinking caps. And it illustrates a very important point. Let's start here. 4 minus pi, positive or negative? Positive, right? So to evaluate the absolute value sign, this bit, we can just take the sign away because what's inside is positive. Yeah, but that negative sign comes from out the front. So we need to hang on to that negative sign. And then we need to apply that negative sign to what's inside the brackets. So, and we won't talk about that now, but you can see that expressions involving absolute value signs don't always come out to be positive. It depends on what else is sitting around them, like this dude. Okay, good. Now, there's another way of defining absolute value, and it's called a piecewise definition. Here is our piecewise definition. It says that if the number inside is positive, just make it A. If the number inside is negative, make it negative A. So let's try and do it for the 3 examples here in example 8. So absolute value of 5. So 5 is playing the role of A. So we look at this bit. Well, 5 is positive, so we're on this top line. So the answer is just 5. So we used the top part of this definition for that one. Let's do negative 3 next. Negative 3 is playing the role of A. Negative 3 is less than 0. So the answer is to make A, whatever it is, negative again. And that's why it worked before. And so our definition is consistent with our number line. And what do we do for 0? Is it top or bottom for 0? Is it the top one or the bottom one? I love how I've just managed to cover up the answer. It's the top one, right? 0 is greater than or equal to 0, so we use the top one. But you can see in this example it actually doesn't matter, because negative 0 is 0. I want you to take a minute and talk to the person next to you about example 9. What is the answer to example 9? Alright, time's up. Someone venture an answer. Minus 70. Everyone get that? Anyone get 50?
I got 50.
Ah, is it minus 70 or 50? Yeah, this isn't voting to work out what the right answer is. One of these is right. It's minus 70. It's not 50. All right, so why the discrepancy? Mathematics, we don't like ambiguity like this. So there's a rule with evaluating algebraic expressions. And if you went to school in South Australia, you probably learnt it as BODMAS. I learnt it as BODMAS. It's just a mnemonic for remembering the order in which you do things. I don't like BODMAS because it has a problem with it that you can read about in the notes. But basically, what you want to do is all groupings first. These are the order of precedence of how you do things. So you perform operations within groupings first. So what that's saying to us is that we needed to work out 2 plus 3 first. So 30 minus 22 plus 3 in brackets is equal to 30 minus 20 times 5. Numbers outside of brackets are just being multiplied together. Evaluate any exponential expressions. There aren't any here. Perform multiplications and division as they occur in order from left to right. So here is a multiplication between the 20 and the 5. So the next line is 30 minus 100. And the final thing is to do additions or subtractions as they occur in order from left to right. So 30 minus 100 is minus 70. Okay, good. How could I change this statement in order to get 50? What could I add or subtract to this statement in terms of symbols in order to get 50? Just in the symbols that it, so in another way, what was the thing that people who got 50 did? Perhaps they did the 30 minus the 20 first, right? And the order of operations doesn't allow us to do that unless that's the very first thing we do. And so we could have put brackets there. And then we would get 10 times 5 and we'd get 50. Don't worry, I've never had a class yet that hasn't been split on whether it's minus 70 or 50. So these give us the rules for evaluating expressions. So 1 minute, person next to you, work out these two expressions following the order of operations. And if you've done that, go on and think about 11 and 12. right, let's do it. So, the first one, what are we going to do first here? The subtraction or the division? Division, good. So, 4 minus 1, and now it's straightforward. All right, this dude, the multiplication first. 1 minus 3 plus 4. What next? Subtraction or addition?
Addition.
Left to right.
Left to right. So even though the subtraction comes first, addition and subtraction have the same level of precedence, so we do them left to right. So 1 minus 3, think about our number line, takes us to minus 2 plus 4. This one works out to be 2. I love these questions. Okay, example 11. We kind of did this before, but tell me, why do these, well firstly, what answers do each of these expressions produce? This one, multiplication first, so this is 2 plus 12 is 14. Over here, groups first, which means brackets, so we work out the 5 times 4, 20. Why do they produce different expressions? What's the difference between them? The brackets. The brackets change the first addition from being the last thing you do to the first thing you do. All right. Number 12 is a bit of a puzzle. I'm going to let you think about that one, and I reckon we'll move on. Now, you might be thinking, why do we care about all of these things to do with numbers? When we start doing algebra, all of these properties still remain true. So we still need to follow order of operations, and we still need to follow other properties of the real numbers. Okay, so the two fundamental operators in mathematics are addition and multiplication. And you can define anything else, any other operation, in terms of those two. So these are our properties or axioms of the real numbers. And mathematicians use fancy words to say things that you can say in plain English sometimes. So the commutative property of addition says, doesn't matter which way you add two numbers together, the result's exactly the same. All right, so let's see. 2 plus 3 equals 3 plus 2. Because don't do that. Because they're both equal to 5, right? Doesn't matter which way you add things together. Absolutely obvious. You can prove it on a real number line. We could be a little bit more fancy about that. If we had another arbitrary value like x, we could do 6x plus 5. Adding 5 to 6x, x is some unknown number, is the same as 5 plus 6x. All right. Does changing order matter for subtraction? Is 3 minus 2 the same as 2 minus 3? No, changing order matters in subtraction. But in addition, it doesn't matter. Multiplication, changing the order when you multiply doesn't affect what you get. 2 times 3 is equal to 3 times 2, and they're both 6. 6 times x is the same as x times 6. Although we don't often write x6, we write 6x, but we'll see that later. Okay, associative property of addition. If you're adding a bunch of things together, it doesn't matter which two you add together first, is what it's saying. Okay, so example. 1 plus 2 plus 3. So you're going to get 3 plus 3, which is 6, is the same as 1 plus 2 plus 3. So you'd evaluate the brackets first and get 5. You'd add 1 to it and you'd get 6. It's earth-shattering stuff. Okay. Associative property of multiplication. When you're multiplying a bunch of things together, it doesn't matter what you multiply together first. 1 times 2 times 3. It's the same as 1 times 2 times 3, and they're all equal to 6 as well. Next one, requires a little bit more attention. So I'm going to scrub these and use this space to talk about the distributive property of multiplication over addition. So what the hell am I talking about? I'm adding two things together and I want to multiply. So I distribute this multiplication over the things that are being added. It's saying that whatever's inside the brackets needs to be multiplied individually by what's on the outside. So, of course, you could work out the brackets first and then multiply, or you could multiply the A through the set of brackets. So the A gets multiplied by the B to give A times B, and the A gets multiplied by the C to give A times C, and then we multiply them together. We're going to come up against this all the time. So it's worth getting our head around. For now, let's look at two numerical examples of this. Okay, so let's do this by grouping first. If we do it by grouping first, it's 2 times 7, which is 14. If we do it by applying the distributive property of multiplication over addition, often just referred to as the distributive property, we do 2 times 3 plus 2 times 4. We work out 2 times 3, which is 6, and we work out 2 plus 4 times 4, which is 8, and then we add our answers, intermediate answers together to get 14. So we can distribute like that. Why is this helpful apart from algebraic reasons? It's one way that people are good at multiplying large numbers together in their head. And this is how you can impress your friends if they're impressed by things like that. So, to give you an example, 15 times 13, people that do quick mental arithmetic will make use of the distributive property. They'll say, well, really, this is 15 times 10 plus 3, because 13 can be written as 10 plus 3. So now I'm going to work out 15 times 10, and I'm going to work out 15 times 3. And this is much easier because it's a multiple of 10, which is why they chose it. 150 plus 45, 195. And they're just doing this rapidly in their head, and that's how they can multiply large numbers together, much larger ones. Works with subtraction too. We could have written 13 as 15 subtract 2. 15 times 15 is 225. If you know your 15 times tables, if you know your 15 times tables, you would have done this. And then 15 times 2 is 30, and you can get the same answer. So it works on subtraction. Okay, so I know we're getting into the tough end of the 2 hours, but if you remember one thing from this hour, remember the distributive property, because it's important. All right, we can do the other ones much quickly because they're obvious. Add 0 to something, it's the same as what you had. It's amazing that mathematicians need to define these things, and that's why it's called the identity property. You're left with what you started with. Identity property of multiplication, if you multiply by 1, you're left with what you started with. We don't need examples, they're obvious. Inverse property of addition, this is how mathematicians define subtraction. So if you've got a number like 5 and you add negative 5, that's like saying go to 5 on the number line and then go in the negative direction 5. Where do you end up? You end up at 0. So this is the opposite process of addition, positive and negative. And the same deal for multiplication. Let me give you a couple of examples because this one gets people sometimes. 5, if I multiply it by 1 on 5, I get 1. Works with fancier expressions too. X minus 3, if I multiply it by 1 on x minus 3, this property says I get 1. Yeah? It's going to come in really handy, that one. But not as handy as the distributive property. Okay, good. have a quick stretch for a minute, and then we'll see how far we're going to get through polynomials. This first lecture is definitely the place that some people are learning everything for the first time, and some people have seen it all before. So we'll get on a much more even footing as the study period goes on. But just hang in there, depending on which level of that spectrum you're at. All right, so we're going to turn our attention to algebraic expressions. So we can use letters to represent numbers, and we saw A and B and C before. If it's representing something that's constant, it's called a constant. If it's representing something that can change, it's called a variable. Sometimes we don't know the value of the constant, but as long as we're sure it's not going to change, it's still a constant. But if we think it's going to vary, or we're not sure what its value is, it's called a variable. Okay, so we're going to work later with letters. But many algebraic expressions involve exponents, and that was the second order precedence we talked about before. And we are going to do some of this in much more detail probably next week, but we need a quick recap before we move on. So here's an example. If we want to multiply 2 together 4 times, there's an easier way of writing that, and that's 2 with a 4 in the exponent or the power. So that's saying 2 appears as a factor here 4 times. We work out 2 to the 4 by actually computing 2 times 2 times 2 times 2, and that gives us 16. So other examples, 5 multiplied together, or 5 appearing as a factor 3 times, 5 times 5 times 5, so you get 25 times 5 is 125, and here are our square numbers. All right, so 9. What's the exponent of 9? So the exponent here is 4, the exponent here is 3, the exponent here is 2. What is the exponent of 9? I haven't written it in yet. It's 1. So I heard someone say you can write it as 3 to the 2, and that's true. But if I just write a number by itself without an exponent, its exponent is 1. It's implied that its exponent is 1. Now, does that fit with our definition? So this says 9 appears as a factor 1 time. Yeah, that makes sense. It's kind of a bit trivial, but it makes sense. So the exponent of 9 is 1. Okay, so the exponent is the power. Okay,